Section 1 Introduction ********** 1. Introduction ******* Over the recent years, there's been a transformative shift in the realm of generative modeling, thanks to large-scale neural networks. These networks now possess a remarkable ability to understand and capture intricate relationships among vast numbers of variables. Think of this like creating a lifelike model of a high-resolution image pixel by pixel, something that seemed nearly impossible until the modern generative networks came into play. The secret sauce behind these networks lies in their strategic breakdown of a mammoth task into more manageable subtasks. Imagine trying to solve a complex puzzle. Instead of trying to fit every piece at once, it's more efficient to categorize and solve bits of it step by step. This strategy helps them evade the infamous curse of dimensionality that tends to complicate matters when dealing with numerous variables. To make it more relatable, imagine two friends, Alice and Bob. Alice has a piece of data, and Bob wishes to receive it using as few bits as possible. So, Alice begins by sending bits of this data to Bob, revealing a little at each step. The better Bob can predict Alice's message, the fewer bits she needs to send him. After each message, Bob refines his next guess based on the new information he has received. The entire process's efficiency is determined by how many bits Alice has to send in total. Let's consider a real-world example. When training a language model, Alice's messages are like chunks of text. Bob's initial guess isn't well informed. But with every new message from Alice, Bob's predictions get sharper, and the overall transmission cost, measured in bits, goes down. This is the essence of autoregressive models, which have proven to be top-notch for language modeling, especially when data has a logical sequence. However, there are certain types of data where autoregressive models don't shine as much. Take images, for instance. Pixels in an image don't have a strict sequence, and this type of model has limitations, like needing many updates to generate samples. Another approach, known as the diffusion model, has shown promise for image generation. In these models, Bob gets slightly altered versions of Alice's previous messages, which are designed in a way that they get closer to the actual data with each transmission. These models function differently, but their underlying principle, in terms of bits and efficiency, is somewhat analogous to the autoregressive models. Diffusion models, despite being good for image generation, have a limitation when it comes to discrete data. The challenge is the noise in the data transmission, which can be quite jarring and discontinuous, especially for textual data. In essence, Bob starts with jumbled up text, with Alice's messages either changing random symbols or leaving them as they are. In this paper, we introduce Bayesian Flow Networks, BFNs. These models differ from diffusion models as they work on the data distribution's parameters rather than noisy versions of the data. This approach ensures the entire generation process is smooth, consistent, and adaptable, even with discrete data. Imagine the data transmission as a relay race. Bob starts with basic knowledge or an input distribution. As the race progresses, he feeds this information into a neural network, which provides him an output distribution. Alice then creates a message based on this and some added noise, which Bob tries to predict and comprehend, constantly updating his input based on Alice's messages. This relay keeps happening for multiple rounds until Bob can predict the data so accurately that Alice can share it noise-free. The beauty of BFNs lies in their dual approach. They combine the strengths of Bayesian inference and deep learning. The former offers an optimal way to gather and summarize information about individual variables, while the latter is a champ at integrating information across many interlinked variables. Furthermore, these networks can function in both discrete and continuous modes. In continuous mode, the flow of information is constant, making it computationally simpler and efficient. Once trained in this mode, a BFN can work in any number of discrete steps, refining its performance with each increase in steps. The upcoming sections of this paper will delve deeper into related work, elaborate on the BFN framework, and share our experiments and results. So, let's embark on this journey. Section Summary. Large-scale neural networks have revolutionized generative modeling by capturing complex relationships among variables. Autoregressive models, flow-based models, deep VAEs, and diffusion models break down the joint distribution into steps, solving a hard problem by splitting it into easy pieces. Diffusion models, unlike autoregressive models, progress from coarse to fine image details as noise decreases, making them more effective for image generation. Bayesian Flow Networks, BFNs, operate on the parameters of a data distribution, ensuring a fully continuous and differentiable generative process even for discrete data. BFNs combine Bayesian inference and deep learning to exploit both individual variable information and contextual information. The continuous time loss function of BFNs removes the need to predefine the number of steps during training and allows for improved performance as the number of steps increases. Section 2. Related work. 2. How this research relates to previous work. Now, when we think about the methods that have been previously developed, the one that comes closest to Bayesian Flow Networks, BFNs, are the diffusion models. But, and this is important, they aren't the same. They have some key differences. To put it simply, function versus data, BFNs are like a bridge. They take you from one type of data distribution to another. In contrast, diffusion models and most of their kin are more like starting points. They begin with raw data and lead you to a distribution. Think of BFNs as a translator between two languages, while diffusion models are like learning a new language from scratch. Continuous versus discrete. One of the cool things about BFNs is that they can work with continuous inputs, even if the data you're feeding them is discrete, like whole numbers. Diffusion models, particularly the discrete ones, usually need discrete samples right from the start. However, there have been efforts to design diffusion models that can handle continuous data. They either convert data to n from a smooth space, or limit the continuous diffusion to a specific range. Our method naturally comes with this continuous aspect, which means it's not just an add-on. This makes things a lot simpler. No need for complicated adjustments or add-ons to make the system learn effectively. Optimization. The magic of BFNs is that they directly focus on optimizing the data's negative log likelihood, unlike some diffusion methods for discrete data, which might need other tweaks to remain stable during learning. Comparison with variational models. When working with continuous data, BFNs are somewhat like cousins to variational diffusion models. Their approach to processing information over time is strikingly similar. However, BFNs are less noisy. Why? Because BFNs start with a fixed foundation, parameters of a fixed prior, while diffusion models often start with something more chaotic, pure noise. We think this might make BFNs learn faster, especially with big datasets, but we need to dig deeper to confirm that. Flexibility. One of the shining features of BFNs is their adaptability. You don't need to design a forward process for them. What this means is, they can easily adjust to different kinds of data distributions. We've tested this, and it's incredible how easily they handle various data forms with minor tweaks in their training routine. This is quite different from other models like discretized diffusion, which often need specially crafted blueprints to operate. So, in essence, Bayesian Flow Networks introduce a new perspective on handling data, bridging the gap between various types of data, and potentially offering a more efficient learning process. Section Summary. Bayesian Flow Networks, BFNs, differ from diffusion models in that they embody a function from one distribution to another, rather than from data to a distribution. BFNs have the advantage of using continuous inputs even with discrete data, unlike discrete diffusion models that use discrete samples as input. BFNs also have less noisy network inputs compared to variational diffusion models, making them potentially faster to learn on large datasets. Additionally, BFNs are more flexible and easier to adapt to different distributions and data types compared to diffusion models. Section 3. Bayesian Flow Networks. 3 Bayesian Flow Networks. 3 Bayesian Flow Networks. In this section, we'll explore the nuts and bolts of Bayesian Flow Networks. Think of it like a guide that breaks down the essential components and methods used to train these networks. Later sections will dive into specific examples for different types of data. 3.1 Understanding input and sender distributions. Imagine you have a set of data, represented by the symbol X. This data has multiple dimensions, which simply means it has many components or values. Each of these values has a corresponding parameter, represented by the symbol theta. The input distribution, symbolized as pi, uses these parameters, theta, to tell us about the probabilities or chances of seeing certain values in our data, x. Think of it like a detailed blueprint that says, given these parameters, here's what you can expect from the data. We can also talk about a sender distribution, symbolized as ps. It has a similar structure as the input distribution but is related to another set of data represented by the symbol y. The interesting bit here is the accuracy parameter, alpha. When alpha is 0, it means the samples from the sender distribution t tell us much about our original data x. But, as we increase alpha, these samples provide more and more clues about bi. 3.2 The role of the output distribution. Now, during the data sharing process, our parameters, theta, come into play along with something called the process time, represented by t. These elements are fed to a neural network called psi. The magic of this neural network is that it processes the input and spits out a new set of values. This output, in turn, helps us determine the output distribution, symbolized as PO. The special thing about this distribution is its ability to use context. While the input distribution simply considers each value in isolation, the output distribution can take into account the entire dataset. It's like when you view a single pixel in an image, it might not mean much. But when you see it in context with its neighboring pixels, the entire image becomes clear. Similarly, in a sentence, understanding one word can sometimes depend on the words that surround it. That's the power of the output distribution. It can utilize this context. Section summary. In this section, the authors introduce the mathematical framework of Bayesian Flow Networks, which includes the structure of functions and distributions required for the model, as well as the loss functions used for training. They provide specific examples of the framework for continuous, discretized, and discrete data. The authors also discuss the input and sender distributions, which are factorized distributions that depend on the parameters and input data. Additionally, they explain the output distribution, which is parameterized by a neural network and can exploit context information. Section 3.3 Receiver Distribution P_R, CDOT, mid, bold symbol, theta, T, alpha. 3.3 Receiver Distribution P_R, CDOT, mid, bold symbol, theta, T, alpha. 3.3 Receiver Distribution Explanation. Let us talk about the receiver's perspective in this communication model. The receiver knows about the sender's way of communicating but doesn't have a clear idea about the sender's exact message. So, how does the receiver make sense of this? Firstly, the receiver has a general idea about how the sender conveys messages. This is like understanding the language but not the specific words being said. This concept is termed as the sender distribution. Secondly, the receiver is exposed to an output distribution, which can be thought of as the outcome of the sender's message given specific conditions. The receiver, not knowing the sender's exact intent, considers all possible messages from the sender and their respective probabilities from this output distribution. Our main takeaway is this. The receiver's understanding hinges on two things: the known uncertainty, which comes from the variability in the sender's way of communicating, which we connect with a parameter called alpha. The unknown uncertainty, which arises from the many possible messages the sender might have intended. 3.4 Understanding Bayesian updates. Now, let us consider updates based on the Bayesian inference. When the sender sends a sample message and the receiver gets it with a certain level of accuracy, denoted by alpha, the parameters the receiver uses to understand this message undergo a change. We term this change as a Bayesian update. But it's not just about one update. Think of it like adjusting your radio to get clearer music. You don't do it just once. You do it multiple times till you get the clearest sound. Similarly, the receiver keeps adjusting or updating these parameters based on every new message from the sender. One interesting feature of these updates, which we prove in later sections, is that these accuracies are additive. In simpler words, if you have two levels of accuracy, you can combine them. This property implies that if you start with a set of parameters and adjust them over a series of received messages, you can effectively combine the accuracy levels of all these messages to understand the final message. Section summary. The receiver distribution, P_R, Y, theta, T, alpha, combines the uncertainty of the sender distribution, P_S, Y, X, alpha, and the output distribution, P_O, X, theta, T, by integrating over all possible sender distributions weighted by the probability given to each sender distribution by the output distribution. The Bayesian update function, H, theta, Y, alpha, computes the updated parameters, theta, by applying Bayesian inference rules. The Bayesian update distribution, P_U, theta, X, alpha, is derived by marginalizing out the sender sample, Y, and has the property that the accuracies are additive, meaning that the probability of observing theta, after drawing a sequence of sender samples with accuracies alpha_1, alpha_2, alpha_n is equal to the probability of observing theta, after drawing a single sender sample with accuracy equal to the sum of alpha_1, alpha_2, alpha_n. Section 3.5 Accuracy Schedule, Beta, T. 3.5 Accuracy Schedule, Beta, T. 3.5 Accuracy Schedule, Beta, T, and imagine you re-updating some data with a continuous stream of new information over time. The amount of accuracy you gain at each moment, which we call accuracy rate, is represented by alpha, T. Over time, this accuracy accumulates, and this cumulative accuracy is what we refer to as the accuracy schedule, beta, T. Mathematically, It's like adding up all the accuracy rates from the beginning of time up to the present. N key takeaway NTHE accuracy schedule increases as time goes on. There are different ways to shape this accuracy schedule for both continuous and discrete data. But we'll dive deeper into that in the next sections. N3.6 Bayesian Flow Distribution FN U200B. And now, once we have this accuracy schedule, we can look at the way our data is updated over time, which we call the Bayesian Flow Distribution. In simpler terms, given our prior knowledge and how our data is updated with new information, the Bayesian Flow Distribution describes the state of our data at any given time. N3.7 Loss function L(x). None major goal in many scientific studies is to minimize errors. The loss function helps us measure these errors. For our study, we look at two types of errors. NHOW, we send data over multiple steps. NHOW, accurately we can reconstruct our original data. NTHE, first error, is a bit complicated. It measures how much information is lost when sending data samples and considers factors like how our data updates over time and the difference in distribution between sender and receiver. NTHE, second error, is simpler. It focuses on how close our reconstructed data is to the original. The smaller the error, the closer our reconstructed data is to the original, making the network's job easier. NTO, get the total error. We just sum these two up. It represents the total amount of information lost when transmitting our data. NTO, tie this all together. This entire process can also be viewed through another lens, that of a variational autoencoder, VAE. In VAE terms, think of our transmitted data as a hidden code. This code has certain probabilities associated with it. The process of sending and receiving data can be seen as encoding and decoding this hidden code. Our loss function essentially measures how well this encoding-decoding process is working. In summary, NWE have a method to continuously update our data accuracy over time. NWE can describe the state of our data at any time using the Bayesian flow distribution. Our goal is to minimize errors when sending and reconstructing our data, and we measure these errors using a loss function. This whole process can be likened to the working of a variational autoencoder. Section summary. The accuracy schedule, beta, t, is a monotonically increasing function of time that represents the accuracy rate at each time step. The Bayesian flow distribution, P_f, theta, x, t, is the marginal distribution over input parameters at time t, defined by the Bayesian update distribution, P_u, theta, theta_0, x, beta, t. The loss function, L(x), is the total number of NATs required to transmit the data and is composed of the n-step discrete time loss, L(n), x, and the reconstruction loss, L(r), x, which are both minimized by matching the output distribution to the data. Section 3.8 Discrete time loss L(n), operator name, math_BF(x), 3.8 Discrete time loss L(n), operator name, math_BF(x). Discrete time loss L(n), x, and what the authors are talking about here is a way to measure loss or error in a discrete setting. Think of this as trying to calculate the difference between your prediction and the actual value at certain fixed time steps. This loss is represented by a rather intricate equation, but what's crucial to understand is that it involves a series of expectations or average values, represented by the big E(s) you see in the equation. Term, DKL, which represents a measure of difference between two probability distributions. One, n, which is just a way of saying they, reconsidering numbers uniformly picked between 1 and n. There's a bit of transformation magic happening with the equations to simplify and relate various terms. The big takeaway here is that through these equations, they found a more efficient way to approximate the original loss without calculating the entire n-step sum, which is computationally expensive. N continuous time loss L(infty, x). In real-world scenarios, it's often more realistic to think in continuous terms rather than in. So, after discussing the discrete time loss, the authors introduce the continuous time counterpart. For this, they've been inspired by variational diffusion models and aim to create a loss function that's not tied to fixed steps and which is simpler and cleaner to use. Essentially, they're trying to transition from a world where everything is measured at set intervals, like looking at your watch every hour on the hour, to a world where everything flows smoothly and continuously, like a steadily flowing river. There's a lot of math involved in making this transition, and that's what all the equations with epsilon, alpha, t, epsilon, and others are about. They are making mathematical tweaks to ensure this transition from discrete to continuous is sound. One interesting aspect they discuss is the D_KL term. This is a measure of how two probability distributions differ from each other. The paper describes how, in their continuous setting, this term can be represented in a much simpler manner. Instead of a complicated mathematical expression, it comes down to the squared difference between two functions, scaled by some factors. And lastly, there's a significant proposition, Proposition 3.1, which provides a foundation for the continuous time loss. It's essentially about how certain probability distributions transform when they smeared out, or convoluted with another. The proof involves some advanced math, but the result supports their earlier discussion and helps validate their continuous time loss function.